So yesterday we talked about the fact that an atom, all we know about the electrons are the probability of where they're located, and that's why the atom looks more like a cloud when we draw the current model instead of the rings or the circles that we see from Bohr's model. And so quantum numbers is a way for us to describe where the electrons are. So these are values that give the most probable location to find an electron. Just like if I wanted to find you, assuming it's not school hours, the most probable place to find you would be your room. So in order to know where that is, I would have to know lots of information like what state do you live in, what city, what street number, that kind of thing. So once I know all of that information, there's a high chance that I could find you there. It's not necessarily where you are, it's just the probability. So quantum numbers are kind of like an electron's address. And just like no two students in this class have the same address, no two electrons can have the same quantum numbers. And keep in mind that quantum numbers are not actually numbers. I'm not sure really why they call it that. Quantum numbers are actually numbers and letters together. So the first quantum number we talked about yesterday was called energy levels. So energy levels represents the cloud size. And another word for that is the rings around the nucleus. So anytime you hear energy levels, you need to think rings. That's the fancy word for these rings that are right here around the nucleus. So if you're in the first energy level, notice how small it is. It's really close to the nucleus. As you move to a different energy level, as you move out, it's going to get bigger. These correspond to horizontal rows on the periodic table. So what I want you to do is look in your reference packet. The very last page has a periodic table, and I want you to go ahead and pause this and take it out so you can label several things on your periodic table. And the first thing to label is these numbers right here. So I want you to start next to hydrogen and put a 1, and then a 2 next to lithium, 3 next to sodium, and keep going all the way down to 7. So what this says is, let's take lithium, which is right here. Lithium, because of this 2 right here, it says that it has a second energy level. So it has 2 different rings around the nucleus, whereas sodium would have 3 rings. The second quantum number, the fancy word for it is sublevels, and when you hear that word I want you to think shape. So for each of these fancy science words I'm going to try to tell you a simpler word that will help you remember it. So for energy levels I want you to think rings. For sublevels you're going to think shape. Now up until now the only shape that we've drawn is a circle, but not all orbitals, which are electron clouds, have a circular shape. Some of them are a little bit different. The names of the shapes are S, P, D, and F, and I'm not sure where they got those letters, but they are important. What I did is I came up with a word for each letter to try to help you remember what it looks like. So for S, when I see a S, I think sphere, because notice that it looks like a sphere right here. For P, it's actually 2 spheres on top of each other, but that doesn't start with a P, so I came up with the word peanut, because if you think of a peanut, it kind of has a top lobe and then a bottom lobe. For a D, it's kind of like a clover leaf, so if you say double peanut, you can kind of see the 2 peanuts perpendicular to each other for a double peanut. And then F is so complicated we actually don't know what it looks like, and I've never seen a picture of it, so you can just put a question mark for that one. So if on your periodic table, what I want you to do is find the first 2 columns. So this looks like 1 in the picture, this green area. It's actually 2 columns, and I want you to put an S on top of those 2 columns. For the 6 columns over here, I want you to put a P, but take a second and make sure that you mark that helium, this one way up here in the top right corner, helium is actually an exception, it's an S. So put a little S next to helium, the rest of it is going to be P. In the middle, between the S and the P, you have the D block, this yellow block right here, and then these last 2 rows that stick off the bottom is called the F block. Go ahead and label that for now, and I'll explain why you're labeling it in just a few minutes. So these correspond to areas on the periodic table. And one little trick that'll get you pretty far is that if you can keep in mind that the energy level, whatever energy level you're in, so like the first energy level, tells you how many sublevels can exist in that area. So for example, in the first energy level, you could only have 1 sublevel, and the first sublevel is S. So in the first ring around the nucleus, it's just a sphere. In the second energy level, you can have 2 sublevels, so it would be S and P. So there's both a sphere and a peanut in the second energy level. In the third energy level, you would have SPD, and then in the fourth energy level, you would have SPD and F. The next quantum number is the orbital, which is the actual region of space for the electron, but you can think of it as direction or orientation. And you keep in mind that 2 electrons can fit into 1 orbital. So for an S shape, the sphere, no matter how you turn it, it's still a sphere, so there's only 1 orbital for that. For a P, you can line it up on the different axes from geometry. So you remember you have the x-axis, the y-axis, and then the z-axis comes out of the paper. So you have 3 different orbitals for a P. And then D and F get a little bit more complicated, but if you can notice the pattern, it's pretty easy. It just goes 1, 3, 5, 7. And because you can fit 2 electrons in 1 orbital, the most you can fit into an S is 2. You can never put 3 electrons into an S orbital. For a peanut, since you have px, py, and pz, you can fit 2 electrons into each one of those orbitals for a total of 6. And you can probably see the pattern. D is going to be 10, and F is going to be 14. The last quantum number is called spin, and this just has to do with the fact that if you have 2 electrons in the same orbital, meaning that they're both, say, in the first orbital or in the first energy level, they're both in the sphere, they have to be going opposite directions. And this is based on Pauli's exclusion principle, which I'll talk about in just a few minutes. So take a minute and pause this and see if you can fill it in. I'm going to walk you through the first one. So for the first energy level, the number of sublevels you can have is 1. So those 2 are going to match. Whatever energy level you're in, that's how many sublevels you can have. The first sublevel name is S. They go in order S, P, D, F. In an S, the most electrons you can have is 2, because it only has 1 orbital. So therefore, the total electrons for the entire first energy level is just 2. So there's nothing you have under the P, D, or F because those don't exist in the first energy level. In the second energy level, you can have 2 sublevels. They would be S and P. You can fit 2 electrons in the S and 6 electrons in the P. So the total for that energy level would be 8. Pause this video for a minute, see if you can fill in 3 and 4, and then check your answers. And check and see how you did. You should have gotten 18 for the third one and 32 for the fourth. Electron configuration is the actual symbols, the numbers and letters that we're going to use to show the electron's address. So just like your address has letters and symbols, this is what we're going to do now. But before we can do that, there's 3 rules that we have to be able to write down. One of them we're going to use today, and the other 2 we'll actually use in our next lesson. So just write down the other 2 for now. The one we're going to use today is called the off-ball principle, and it says that electrons always occupy the lowest energy level available. So we call it the building up principle. And what that means is that you always have an electron in the closest energy level possible before you fill up a higher one. So for example, if you just have 1 electron, you wouldn't put it in the second energy level. You always put it in the first one. Pauli's exclusion principle will actually come into play in our next lesson. For now, just write down it's that if 2 electrons are in the same orbital, they have to have opposite spins. And that's because no 2 electrons can have the same 4 quantum numbers. And the last one is called Hund's rule. I call it the fair share rule. So what I have in quotation for each of these are 2 words that try to simplify the definitions. So long definitions are really hard to memorize. 2 words is a whole lot easier. Hund's rule we'll actually get to in our next lesson as well, so just write that one down for now. Hund's rule says that each orbital in a sublevel must have 1 electron before any orbital can have a second. This is what an electron configuration looks like. Now, a lot of students get really good at being able to write this, and in fact, hopefully by the end of the day, you'll be able to do this pretty easily. But what they don't understand is what they're doing and why. So I want you to be a better chemist than that, and I want you to understand what these symbols are actually telling us. So let's start with the coefficients, and remember that word for math is just the big number in front of a variable. So this coefficient here tells you what energy level the electrons are in. So this one describes the first energy level, this is the second energy level, so we've moved out a little bit. The letters tell you the sublevel, and remember that's a fancy way to say shape. So this is describing a peanut shape that's the second distance from the nucleus. This S is describing a sphere shape, and it's the first distance from the nucleus. So the big number in the letter describes the region of space. The exponent that's sitting up there is not really an exponent, but it looks like one. The exponent tells you how many electrons are occupying that region of space. So this shows that there's 2 electrons in this sphere, which makes sense because you can fit 2 electrons into a sphere. You can't fit 3, but you can fit 2. For the p, notice that there's 4 over here, and that's okay because p can hold up to 6. So let me show you how to do this. The first thing you're going to do is find carbon on the periodic table. It's kind of in the top right area. And then you want to go up to the top left next to hydrogen, and you're going to start with hydrogen at 1, because if you notice next to it, there's a 1 next to it. On top of hydrogen, you should have an S that you labeled the S region. So it's 1s, and you can fit 2 electrons. So you're going to count 1 for hydrogen and 2 for helium. I'm going to go ahead and put the answer so we can talk about it. So this is the top row of the periodic table. 1 is to the left of it, S is on top, and you count 1, 2 to get this little 2 over here. Then you're going to go down a row because we finished the complete top row. So now you're next to lithium. Next to lithium you should have a 2. You're still in the S shape, and if you count across, you should have 1 for lithium and 2 for beryllium. So these 2 come from the 2 that are in the S area there. Keep on going all the way across the row, and you should get to another 2. So you're still in the 2 row, but now you're in the P section. And in fact, you can go ahead and put a little 2 on your periodic table next to B boron. And then if you count over, carbon is only 2 across, and that's why this P only has 2 right here instead of 6. Let's try argon. First we're going to start in the top left again, so we have a 1 next to hydrogen. It's in the S region, and if you count across it goes 1, 2. 1 for hydrogen and 2 for helium. And that's how I got this 1s2 right here. Then you go down a row, and now we're in the 2. So we're going to do 2s and count across 1, 2, and that gets us to beryllium. Keep on going all the way across the row to boron, and you get to another 2. But now we're in the P section, and we're going to go all the way across the P section, and if you count, you should see that it's 6. Then we're going to go down another row, and you get to 3. We're still in the S section, and if you count across from sodium, it should be 1, 2. Keep on going all the way across the row till you get to aluminum, and next to aluminum you might want to put a little 3, just to remind yourself that it's still 3 there. And if you count across to argon, you have to go all the way over to 6. Let's look at fluorine. Fluorine's the same kind of thing. Start at the top left, and for hydrogen and helium you get 1s2. Go down 1 row, and you've got 2s2. That gets you to beryllium. And then for fluorine, we're going to stop at 2p5, so we're not going to go all the way across. Now for germanium, it's a little bit different. Let me go back 1. So for germanium, we're going to have to go through the D section, and there's one thing that I didn't mention yet, and that is that there's some overlap for D. So right here between calcium and scandium, I want you to put a 3. Right here I want you to put a 4, and right here I want you to put a 5, and here put a 6. So when you're doing the electron configuration, you get down here. Notice that there should be a 4 next to K, so it's 4s, 1, 2. It's tempting to say 4d, but you're actually going to go 3d across here. And then once you finish zinc, then you would go back up to 4. Try germanium and potassium. Pause this video and try those 2 and then check your answers. And the last thing is that there's actually an abbreviated way to do it. And for the abbreviation, what you're going to do is start on the element, go up 1 row and all the way over to the right and choose that element to put in brackets. And then you can start with the element directly after the brackets. So then you would start with whatever element comes next. And this is one of those topics that's difficult to explain online, so please come in and see me if you've been absent, and I will definitely go over this with you in class. Thanks a lot.